Today, I wanted to talk about a subject that is dear to my heart, which is optimizing or finding the best possible, most ideal objects in some sense for surfaces. And, oh, thank you, yeah, it was a little loud. Of course, in order to, so the title is Best Possible Shapes of Surfaces. I'm going to have to explain what I mean by shapes and what I mean by possible shapes and what I mean by best possible shapes. So the first part of the talk will be explaining how this problem can be approached as a mathematics problem rather than just a purely aesthetic problem, which is the way you would think of it when you first see the title. And then talk about the challenges that mathematics problem has presented to us for many years and what progress we've been able to make on it. It's not a solved problem by any means. In fact, there's a lot of argument about what it would mean to actually completely solve the problem. So let me get started. Well, first I have to tell you what I mean by a shape and how we describe what a shape is. But maybe I better talk about the objects that I intend to talk about, the surfaces. There are lots of different possible topologies for a surface. And for me, a surface is always going to be a smooth two-dimensional object without boundary, compact, that is bounded and closed. It doesn't have any pieces going off to infinity. And there's a famous theorem that says that every orientable surface in 3 space is either a sphere like this, or it's a torus or a connected sum of 2 tori or connected sum of 3 tori continuing on down. There's we say the number of connected tori that you add together is called the genus. G, this would be G equals 0, no tori. This is G equals 1, G equals 2, G equals 3. And that's one series of these surfaces that have no boundary and are closed. But there's also another series of surfaces that are distinguished from these by being not orientable. This is the analog of the Möbius band that you may have heard of that has only one side. If you start out outside here and trace around and go through the hole here, you'll come back. You'll be on the inside of the bottle. This Klein bottle is one actually of an infinite series, just like this. These are one of an infinite series. This is the first few terms of an infinite series of surfaces. I'm going to be interested in both the orientable and the non-orientable case, but I'll have more to say about the non-orientable case a little later. The question that I want to raise and I want to discuss how it can be formulated mathematically and what that means is for each one of these surfaces, is there a best possible shape for it? I mean, for the sphere, it's pretty clear that a round sphere is about the best you could ever imagine representing the sphere. But for something like this, for example, maybe this is not the best way, maybe this is not the best shape for a surface, or maybe this is, even though this is a traditional picture of a Klein bottle, maybe this is not the best possible shape of a Klein bottle. Maybe there's something that's more aesthetically pleasing than these pictures. But of course, in order to talk about that, I have to give a meaning to the word best. And best is going to be I'm going to define some way of measuring how bent a surface is, how far away it is from being a nice, round, or flat surface. I'm going to introduce a way to talk about that and then ask what's the best possible way I can arrange a surface so as to get the minimum amount of bending or distortion to make it look as nice as possible. So to do that, I need to say a little bit about how geometers describe the shape of a surface at a given point. You know, a surface, imagine this, like this brown sheet here, this surface has the property that if you pick a point on the surface and you look at the best approximating tangent plane, so that you have a normal perpendicular to the plane, if you look at the surface, there'll be one direction in which it bends the most in one direction and maybe the other. For example, if the surface is saddle-shaped, there'll be one particular direction where it bends up the most, and then perpendicular to it, there'll be a direction where it bends down the most. Those are called the two principal directions. They don't always have to be one going up and one going down. It could be something like this instead. You might have a surface that looks wide and thin like this, so that it's narrow in this direction and wider in this direction, so that this is the place where it's the most curved and this is the place where it's the least curved. And the curve that when I talk about this number that I'm associating to this point here, in this case kappa 1 would be this way and kappa 2 would be this way. The curve, what you should imagine is that at each point we're approximating this principal curve by a circle. And we look at the best approximating circle of radius r, and kappa is 1 over r. The idea is that as r goes to 0, as r goes to 0, the surface is getting more and more tightly curved, and as r goes to infinity, the surface is widening out. This is a case where kappa 1 and kappa 2 are both positive. I can always, one of those numbers is always greater than or equal to the other. This is a case where they're both positive, but in that case, the saddle-shaped surface like that, what you'll find is that kappa 1 is positive, but kappa 2 is negative at this point where there's a saddle. Now, the sphere has the property that at every point, it's extremely round, and it has the property that at every point, kappa 1 and kappa 2 are equal. Points like this are called umbilic points. And because the curvature is the same in every direction. Now, obviously, that's a very symmetric property for a surface to have, is to have its curvature all the same in every direction at every point. And what we're going to do to measure the distortion of a surface is we're going to look at how badly we have to get away from making everything umbilic. That is, a distortion will mean that one of the curvatures is bigger than the other. And what I want to do is find the surface in some sense that has the least distortion for a given topological type. Find the way of presenting it so that it has the least total distortion. But I have to say what I mean by total distortion. So let's go to that. Well, of course, knowing what happens at one point doesn't really tell you much about what happens over the whole surface. But what we can do instead is do this. If you have a surface, you choose some function of the two curvatures, kappa 1 and kappa 2, and just integrate it over the surface, where this is the area measure of the surface. And so what this does is it takes the total accumulated function of curvature and gives you a number, which is, you can think of it as sort of the total measure, a total measure of curvature. But of course, that depends on what this function is here. A naive thing to do would be, for example, to take the function to be 1. If you just put a 1 here, then you're just integrating over the surface the area, which basically just adds up the total area of the surface. And so in that case, the mu of 1 is the total area of the surface. And that doesn't really tell you much about the shape, right? I mean, you can have a surface of fixed area and you can dent it in and it'll still have the same area. That's not going to control the shape very well. And so that's not going to be a very good measure of shape for us. On the other hand, there's another problem, which is that if you take a surface and you double it in size, what will happen is that the curvatures will all go down by a factor of 2, because every time you magnify, the circle that's approximating it will magnify its radius by that same amount, and 1 over it will decrease by that same amount. So when you magnify by a factor of r, the curvatures magnify by a multiple of r, and the area, though, the area magnifies by the curvatures. There's a misprint there. That should be well, that's r to the d, right? If it's a function, that's not a misprint. That's what it is. The curvatures will go down by a factor of r, each one, but the area will go up by a factor of 2. So what will happen to the measure if f happens to be homogeneous of a fixed degree, say degree d, then what will happen when you perform this integral over a scaled surface scaled by a factor of r, the total measure of the surface, this overall shape measure, is going to be r to the 2 minus d. 2 for the area going up by a factor of 2 by r squared, and minus d for the fact that the curvatures go down by a factor of d. The individual curvatures go down by a factor of d. So unless d is 2, just by scaling the surface, this function, if I use a function that's homogeneous like this, just by scaling the surface, I'll get, there won't be, I can make the thing as large or as small as I like without changing the actual shape. It just changes by scale. The way to get rid of the scale problem is to choose d to be 2. That is, choose a function that's homogeneous of degree 2 in kappa 1 and kappa 2, and then this measure of shape, whatever it is, will not change when you scale. So that puts a pretty severe restriction. There's one more thing that I should have warned you about, is that, let me go back. I should have warned you that these two functions, kappa 1 and kappa 2, on their own, unfortunately, when you compute them, you have to take square roots, because you're taking the root of a quadratic equation to find them, and so they themselves are not smooth. The kappa 1 and kappa 2 aren't smooth. They can actually be, they can't be discontinuous, but they can fail to be even continuously differentiable. However, the sum and the product of kappa 1 and kappa 2 are smooth. So if we write something that's in terms of this, which is called the mean curvature, which is the average of the two curvatures, principal curvatures, or if you take the product, which is called the Gauss curvature, those two are in fact smooth functions. Now, so you might say, well, why don't I just take a nice candidate would be to take f to be kappa 1 times kappa 2. If I take kappa 1 times kappa 2, that's homogeneous of degree 2, and so the integral of kappa 1 times kappa 2 times dA, that'll give me a measure, that maybe will give me a measure of the shape of the surface. However, there's a famous theorem, the Gauss-Bonnet theorem, that tells us that in fact that particular combination doesn't tell you anything about the shape of the surface. In fact, all it does, the Gauss-Bonnet theorem says that if you integrate the product of the principal curvatures, that is, you integrate k over the surface, it always comes out to be 2 pi times a whole number, an integer called the Euler characteristic of the surface. The Euler characteristic turns out to be, for orientable surface, say if it's a G-hole torus like this, then the Euler characteristic is twice 1 minus the genus, the number of holes. So for example, the Euler characteristic of the sphere is 2. And so according to the Gauss-Bonnet theorem, no matter what the shape of the sphere is, the 2 sphere is, this integral will always give you 4 pi. There's no, so it will not control the shape of the surface at all, unfortunately. So that particular thing won't work. H was homogeneous of degree 1, so one thing we could do to get something homogeneous of degree 2 would be to square H, and then we'd get something that's homogeneous of degree 2, and maybe that will be something we can work with. Well, in fact, there's several things that you can imagine doing. For example, you could take the sum of the squares of kappa 1 and kappa 2. That's homogeneous of degree 2. Or you could take the difference squared, which is homogeneous of degree 2. Or you could take, like I was saying, h squared, which is homogeneous with degree 2. But of course, those three functions, the only difference between these functions is that there's some multiple of kappa 1, kappa 2. Right? So for example, kappa 1 squared minus kappa 2 squared is kappa 1 squared plus kappa 2 squared minus twice kappa 1, kappa 2. So in fact, that term will just pass over by the Gauss-Bonnet theorem and give us a constant term that doesn't tell us anything about the shape. So I could, for example, take the sum of the squares of the principal curvatures and integrate it, or I could look at the difference, the square of the difference of the principal curvatures and integrate it, and I'll be off by a constant. And that constant, and if I'm saying I want the thing with the least whatever, minimizing this is the same as minimizing this. And similarly, minimizing the integral of the square of the mean curvature, after you remember h has a 1/2 kappa 1 plus kappa 2 in it. That's why that 4 is there to make the leading terms work out the same as over here. That also differs by a constant. So any one of these quantities here that I want to minimize, it'll be minimized for the others because they all differ by these things that don't depend on the shape. So, but one thing you can see right away from this is just from this equation here is that this integral, because it's a square, this is a square and it's never negative. And it's equal to 0 if and only if the two curvatures are equal. That is, it's umbilic everywhere. So the lowest this can ever be on any surface is 0. The lowest this can ever be on any surface is 0. And if it's a two-sphere, you know that this is 8 pi and that's a minus 8 pi. And so when you solve for the integral of h squared here, what you'll find out is that for a two-sphere, this integral is always at least 4 pi. So the integral of the square of the mean curvature over a two-sphere is always at least 4 pi, and the only way you can have equality is if the sphere is a round two-sphere, because the only way you can have equality is when kappa 1 minus kappa 2 is 0 everywhere, and if it's 0 everywhere, it's an umbilic sphere, and so it's a round sphere. So that's a good sign. That means that minimizing, say, the integral of h squared is at least it gives the right answer for the two-sphere. Because when you take the two-sphere, the lowest possible sort of measure of bendedness, the lowest possible value is 4 pi, and that happens exactly for the round spheres and no others. So that's a good first test case. So the natural thing to ask is, what happens next? The next simplest surface is the torus, and that is the donut that I drew earlier. And there's a famous paper by Thomas J. Wilmore in 1965, in which he conjectured, after doing some calculations, and I'll say what that means, he conjectured that if you start with a torus, that is a donut, a ring-shaped thing, then the integral of h squared is always at least 2 pi squared, and with equality if and only if it's an anchor ring with aspect ratio 1 to square root 2. And what do I mean by an anchor ring? I mean take a circle and revolve it around an axis. Say centered, if you take the circle and revolve it around an axis, you'll sweep out what's called an anchor ring surface. And the picture that I didn't draw here but should have is, so you take a circle, and because scaling doesn't matter, we can assume the radius of the circle is 1, and the only thing that matters is the distance from the axis of rotation. And it turns out that if you take a circle of radius 1 whose center is square root 2 from the axis of rotation, you get, and compute this number, you get exactly 2 pi squared. And if you move the circle further away, or you move it closer, either one, this integral goes up. That is, if you, among all these anchor ring rotation surfaces, the one that gets the lowest value is where that ratio is 1 to square root 2. And there's a picture of what it looks like, 1 to square root 2. You might ask, why square root 2? I mean, it seems, usually you have some intuitive picture of why that should be the best one, but it's not so obvious when you look at it like this. And you might wonder, how did Wilmore conjecture that this ought to be the right thing? Well, what he said, I talked to him once. What he said was, the right answer has to be the most symmetric thing you can imagine. And the most symmetric thing I could imagine was taking a circle and revolving it around a line. I couldn't think of anything that was more symmetric than that. And I tried all the circles revolved around lines, and this is the one that works. This is the one that gives the minimum. And he also tested, suppose you take a curve in space and take a tube of fixed radius around the curve. I'll say more about this a little later, but he checked the case of a tube around a closed curve in space and found out that always gave at least 2 pi squared. So 2 pieces of evidence, that's enough for a conjecture. And so he made this conjecture that this was the best, and for the longest time, people didn't know any better than this. While I'm at it, I'll just say because of Wilmore's paper, he raised this question of for anything, not just a torus. He wanted to find the best possible shape for every surface, and he raised this question. And you know, in the calculus of variations, when you're trying to find a minimum, the trick, just like in first year calculus, when you're trying to find the minimum, the first thing you do is find all the critical points. And once you find the critical points, then you test each critical point and find the minimum, right? I'm sorry to say that's the prevalent strategy no matter how far you go in differential geometry, is find the critical points and then once you understand all the critical points, find the minimum. So in his honor, the surfaces that are critical for this function, integral of h squared, are called Wilmore surfaces now. And of course, the round sphere is a Wilmore surface. It's not clear that there are any others. We know what the minimum is, but there might be other critical points. Right. But then a really funny thing happened that turned up. And it has to do with doing things. So far, we've talked about the fact that you can translate and rotate, and you can scale, and it won't change the Wilmore function. Well, it turned out if you can do more than that, because if you take inversion centered on a point, that is, so the idea here is if you pick a point in Euclidean 3 space. And then invert in the sphere, in the unit sphere centered in that point. That is, every point x, you divide by the square norm of x. So that if x is less than 1 in size, it gets really big. And if x is norm 1, it stays norm 1. And if x is bigger than norm 1, it gets moved inside the sphere. Here I'm doing it for any point, but you can just imagine p is 0. And what we're doing, this so-called inversion centered at P, is this is exactly what it means to take a point and invert it with respect to the sphere centered at P. It's just the formula. And the set of all these transformations have the property that, just like those of you who've studied complex variables, in one complex variable, you know the linear fractional transformations are conformal. That is, they don't preserve lengths, but they preserve angles. Well, the same thing is true for inversions. They preserve angles, but not lengths. And it turns out that every transformation that preserves angles is a composition of translations, rotations, scaling, and inversions. So this collection of transformations, the conformal transformations, sort of the three-dimensional analog of linear fractional transformations, called the conformal group, and it turns out that there's a 10-parameter family of conformal transformations. So it's a lot bigger than you might guess at first glance. And here's just a picture of another way you can think of conformal transformations and the thing you can think about is, of course, conformal transformations aren't actually defined at the point P, because the point P, there's no obvious point to send it to. But it turns out that if you just add a point at infinity, which the usual way of doing this, just like you learn in complex variables, is you do stereographic projection to roll the plane, where in this case a three-dimensional space, up into a three-sphere, then inversion just switches the point that you're inverting at with infinity and back and forth. And it turns out that that's smooth, just like in the case of just like in one complex variable, inversion z goes to 1 over z actually extends smoothly to the Riemann sphere and is conformal, right? So the same thing happens in 3 dimensions. That's not so. Now, why am I bringing that up? It's because of the following kind of amazing fact that if you take a surface in 3 space that doesn't contain a particular point, and then you invert in a sphere around that point and get a new surface, then it turns out that this quantity doesn't change. That is, the square of the difference of the principal curvatures times the measure of area, that quantity stays the same when you make this transformation, when you do inversion. And therefore, the integral is not affected by inversion. And since every conformal transformation is generated by translations, rotations, scaling, and inversion, that means that every conformal transformation won't affect this integral. So this Wilmore function, this Wilmore measure of bending, is invariant under conformal transformations. And that caused a kind of an interesting, made you realize something interesting. So that's what I'm saying. The Wilmore function is, we call conformally invariant. So it's kind of a measure, in some sense, it's kind of like a conformal measure of area. Anyway, but what you can see, though, is that it means that Wilmore's original conjecture can't quite be right. Because if you just take a round anchor ring torus and invert it in some off-center sphere, the resulting thing won't be an anchor ring torus anymore. It'll be big on one side and small on the other, but it won't have changed the Wilmore function. So if we start with a Wilmore torus, that is 2 pi squared, this guy will also integrate to 2 pi squared. And in fact, it turns out that, depending on how you center things and choose your scaling and things like that, you can make the hole here as small as you like. You can make the hole really tiny while the rest of it blows out to become more and more like a sphere. In fact, you can take a sequence of these things that approaches the sphere as a point set without much sweat. And so when you're just doing things like this, where you can have the bending accumulate near a single point and the handle just squeezes off, this you can actually converge on a sphere. That is, you can lose the topology. The integral doesn't help you keep from things pinching off. That is, minimizing the integral. So the standard strategy in the calculus of variations of, for example, showing that there's a minimum by saying, well, there is an infimum. Every set of positive numbers has an infimum. There is an infimum, so take a sequence of things whose Wilmore energies converge to the minimum, and then try and select a convergent subsequence. That's the standard strategy. But that won't work in this case, because you can have a sequence of things like this that converges to a sphere, even though the integrals aren't converging. So this turns out to be a problem, and it's one of the reasons that the Wilmore function was so interesting is because it has such a large symmetry group that the natural things to try don't work to be able to produce a minimum. And this was, of course, a big source of consternation because people wanted to know, how can we find the best possible shape if we don't even know there is a best possible shape? Because it could be that every time you take a minimizing sequence, it always blows off the handles, and you wind up converging to a sphere. That would be really annoying if that were the case, because that would mean that the question, at least for this measure of best possible shape, that there couldn't be an answer. Right? But people didn't know what to do. However, it became clear that this extra symmetry was a key to understanding the problem. This fact that there's this larger symmetry group that you have to somehow or another take account of had to be understood before we could hope to make any progress on the problem. And for that reason, it turns out that it's important that there's two views of adding this point at infinity to E3. One is this, as I was saying, just use stereographic projection to make it into a three-sphere, and then the symmetries of the rotation, the symmetry of the rotation of this three-sphere in 4 space is just the orthogonal rotations in 4 space. And that's a pretty big group. That's a 6-dimensional group, but it's not nearly as big as the conformal transformations. And in fact, there's another picture, rather than thinking of it as a three-sphere, S3 sitting in E4, you can also think of it, it turns out, as the set of null light rays in a Lorentzian 5 space, sorry. If you think of L41, so the inner product is minus x0 squared plus x1 squared plus x2 squared plus x3 squared plus x4 squared, then the set of null rays actually forms a three-sphere. You can imagine, for example, slicing it with norm x is 0 and say x0 is 1, and you get a three-sphere here. But now, if you think of the null rays and you look at the linear transformations that preserve this quadratic form, the Lorentz 4 space, you can see what the conformal symmetries look like. The conformal symmetries turn out to be this 10-dimensional group that's the orthogonal transformations for an inner product of signature of type 4-1, and the plus just means that I'm considering things that preserve the forward light cone rather than the negative light cone, which I don't care about. Anyway, both of those views turn out to be important. One of them points out that, for example, because Lorentz transformations allow you to have two fixed points, that one repelling and one converging, when you look at it over here, what it says is that one conformal transformation, one way you can have conformal transformations is you can fix the North Pole and the South Pole, and you can just scale from. This is the picture that you get when you look when you think of scaling. When you look at what scaling does in Euclidean space, when you complete it to infinity, it fixes the origin and the North Pole, but it just slides the spheres up and down and preserves the conformal structure. And we're going to need that fact in a few minutes. There's another important formula that I want to mention. It turns out that was really important for further work in this process, which is that it turns out that if you identify a surface, if you take now in Euclidean space here, this is E3, and you take some surface, and you look at its stereographic projection up here, call this S and call this S bar. So this gets stereographically projected down here. Then it turns out that, of course, S bar sitting inside the 3-sphere, which is sitting inside 4 space, S bar has a natural notion of a mean curvature, that is curvature in the direction of the tangent to the 3-sphere, and because the 3-sphere is so round, there's a 1 that comes from the bending that's caused by the 3-sphere sitting in R3. It turns out that the Wilmore functional on S, which is the integral of h squared dA, when you pull it back over here, when you look at it over here, it turns out that that works out to be the integral over S bar of the mean curvature in the sphere plus 1 times the area in the sphere, which, because this mean curvature squared is always greater than or equal to 0, that's greater than or equal to just the integral of the area. So it's greater than or equal to the area of the surface, of the image surface on the sphere. And this turns out to be an important estimate that says that this observation of Li and Yao, that the Wilmore functional of S, the Wilmore measure of S, is always at least as large as the area of any lifted, pre-image under the stereographic projection in the 3-sphere. It's at least that large. That has some interesting consequences because, for example, if you now take a surface like this, take a surface, fix a point on the surface up here, and start dilating away from this surface by conformal transformation to the opposite point. Call that P and call it P bar. If you just start dilating away, what will happen is that the surface will converge. The surface will converge to pretty much everything outside the little ball will get contracted around to this ball back here. Because as you dilate away, everything gets contracted, and this part actually converges to basically a great sphere. So one of the limits, once you lift the sphere up and then dilate away, one of the limits will be basically a great sphere, which we know the area of a great sphere is 4 pi. Now, if the surface is actually passing through itself more than once, suppose, for example, that instead it does something like this, and there's 2 sheets that go through each other. Then when you dilate away from this point, it'll converge to 2 spheres. And so the area will converge on 8 pi. And in general, if S passes through some point m times, then this argument shows that the Wilmore function, which is always at least the area of one of these pre-images, has to be at least 4 pi m, where that's the number of pre-images. So you get 2 interesting corollaries of this, neither of which is obvious. The first is that if the Wilmore integrand is less than 8 pi, then the surface has to be embedded. It can't cross over itself, right? Because if it ever crossed over itself, you get at least 8 pi. So, whoops, I backed up. So if you can guarantee that you're down below 8 pi, you're guaranteed your surface is embedded, and that's something you wouldn't see without having this argument. And the other thing is that gives us our first estimate for the Wilmore functional of RP2. I don't know how many of you know what RP2 is, but it's if you take the 2-sphere and identify opposite points, then you get something called real projective space, or the real projective plane. And it's a surface. It's one of these non-orientable surfaces that I didn't draw the picture of. We'll see it again. And there's a theorem in topology that says that any time that RP2 appears in 3 space, it has to have a triple intersection. That is, there have to be three sheets that come together in one point. This is a theorem, I think, I forget who proved it. It was proved maybe in the 40s. May have been Whitney. I'm sorry, I didn't look it up. But it does give us an estimate that says that the Wilmore function of RP2 is at least 12 pi. Well, so what does that tell us? I think, let's see, given the time, I think I might skip, I'll just say very briefly what this is because I don't want to skip it completely. Li and Yao also realized at that time that maybe one approach to proving the Wilmore conjecture was to first consider the problem given a surface in given the surface in the three-sphere, and you look at all conformal transformations, find the biggest area that it has, stretch it, move it so that it's as stretched out as possible using conformal transformations, and that will always be a lower bound for the Wilmore functional. So what they did was say, well, maybe we can figure out for any conformal immersion of a surface, maybe we can figure out actually this should be the infimum of all conformal immersions of the maximum area of the, right? And so that turned out to be an interesting approach because the conformal structures on the torus, it turns out, those of you who've studied some complex variables know that the conformal structures on the torus there's a two-parameter family of them. And if you fix the conformal structure, a conformal structure on a torus is, you can think of it as C modulo a lattice, where the lattice is generated by 1 and a complex number with positive imaginary part that fits into this region. That's where tau fits. And what Li and Yao showed was that this quantity is at least 2 pi squared over y if y is less than or equal to 1. And the consequence was that if the conformal structure induced on the torus is in this little piece right down here, where y is less than or equal to 1, then the Wilmore conjecture is true, right? If you insist that the conformal structure fits in this little curvy triangle down here, where y is less than or equal to 1, then this number is bigger than or equal to 2 pi squared. This number is any Wilmore immersion is at least this large. And so they proved the Wilmore conjecture for tori way down here. Of course, there's this huge region where it didn't give any information. But it was a start. It was the first real confirmation. In particular, the square torus, which is what the anchor ring torus is. The square torus, which is right there, has its conformal volume is at least 2 pi squared, and so the Wilmore conjecture is true for the square torus, which is a nice result. But it didn't help. For example, just a little bit above that, it goes down instead of up, so it's not helpful. This conformal volume was a really new, really interesting and useful idea. And a lot of people worked on it, thought about it. In 1986, Montiel and Ross, that's a misprint there. There shouldn't be two S's there. It's Montiel and Ross. They gave an estimate for the conformal volume, again, in a slightly bigger region. And I was able to prove that conjecture. But unfortunately, it made the region larger where we had an estimate for the conformal volume, but it turned out not to help for the Wilmore conjecture. It was useful for other things, but and it's an illustration of how working on one problem actually turns out to lead you to other interesting problems that then turn out to be useful for other things. But I don't have time to go into that. I realize I only have about 14 minutes left, so I'm gonna not talk about that. Let me just say what we knew about the Wilmore conjecture up until fairly recently. First, as I mentioned, in 1965, Wilmore proved that if it was a tube about a curve, if your torus is a tube around a curve, then the Wilmore measure is at least 2 pi squared. And in 1984, Langer and Singer showed that if it was a torus of revolution, we were using just a circle to revolve, but you can take any curve in the plane, any closed curve in the plane, in a half plane, and revolve it around the edge. And they proved that the Wilmore, that WT2 is always at least 2 pi squared in that case. Then there was a big breakthrough in 1993 when Leon Simon proved that there is a minimum. That there actually is that it's possible to choose a sequence that goes down to the minimum that doesn't collapse the handle. And I'll say a little bit about what that, just to give you an idea of what's involved, I'll say a little bit about what that is. But before I say that, let me warn you that there's going to be a big gap between 1993 and when the next real progress on the Wilmore problem is made. The fundamental idea for existence, though, decides, it says, instead of cursing conformal invariance, which is what's causing the handles to be collapsible without you being able to control them, use it for something. And the idea was this. In 1970, Blaine Lawson had actually constructed for every genus an embedded minimal, that is h equals 0, h bar equals 0, G-hold torus in the 3-sphere with area less than 8 pi. So what that meant, since h was 0, the Wilmore integram was the area on the sphere. So, and since the area is less than 8 pi, what that proved is that wherever the infimum occurs, as soon as you get down below 8 pi, I mean, when you're converging, you're not going to deal with anything except embedded surfaces. You only need to deal with embedded surfaces. Then there's a beautiful theorem that says that if you have an embedded surface in the 3-sphere, you can always conformally move it to where the maximum volume is achieved, the maximum area is achieved. And there's a canonical way to do it, and you can sort of conformally maximize anything by using the conformal transformation. And you need embedded because of the following annoying thing. If you're on the sphere, let me just, right here. Suppose you're on the sphere, I'll just draw it here. And you take two umbilic spheres that are tangent to each other. If you take two umbilic spheres that are tangent to each other, well, if you start out with them being small, of course they don't have area anywhere near 4 pi. If they're umbilic spheres, their area is less than 4 pi. And so, but because they're tangent to each other, they're not equal. No matter how you dilate away from here, you can't make both of them a great sphere. So the total area, no matter how you conformally transform it, will stay less than 8 pi. It'll get as close to 8 pi as you want, but it'll never equal 8 pi. So you cannot achieve the maximum when it's not embedded. But when it's embedded, you can always conformally transform to get up to the maximum. And you say that a surface is conformally maximized if the area is greater than or equal to that of any of its conformal transforms. And because we know we're dealing with embedded surfaces, what we can do is we can take a sequence of conformally maximized G-hold embedded tori such that their Wilmore integrals converge to the minimum, to the infimum, which we know is less than 8 pi. And once you have the conformal maximization, I can't really give the proof now, but it prevents handles from pinching off. Once you know that you've balanced everything to make it conformally maximized. And so when you converge, nothing goes wrong with the topology. And so you prove that there is a minimum. There's a minimum. And it actually converges to the actual, there's a convergent subsequence that actually converges. So we know there is a best possible shape. That was Leon Simon's idea. It's a beautiful idea. But unfortunately, it doesn't tell us what the minimum is. It only tells us that it's there. I want to back off for just a minute or two and talk about the critical points for the two-sphere, which is something that we know what the minimum is. The minimum is the round sphere. But are there any other critical points? See, another possible approach would be if there's only one critical point. You could guess, well, maybe there's only one critical point. And if there's only one critical point, then one thing that could possibly work to give a proof would be to flow down the gradient lines of the Wilmore functional and converge to a minimum. You won't get stuck anywhere because there's no other critical points, hopefully. Well, unfortunately, even for the round two-sphere, that's not the case. In 1984, I actually showed, I studied the problem of what are the Wilmore spheres, that is, critical points for the Wilmore functional is topologically a sphere, and I showed that if you take a surface of genus 0, that is a sphere, and it's an immersed Wilmore surface, then there is a point somewhere in 3 space so that sigma passes through P a total of some number of times bigger than 0, and such that when you take that point out and invert, the result is a complete minimal surface with flat embedded ends. And moreover, the Wilmore integral is exactly 4 pi m, which we know is at least 4 pi m by Li and Yao, but it actually equals 4 pi m in that case. So the Wilmore spheres are actually very rigid, very constrained. They basically come from minimal surfaces in 3 space with flat ends. And what do I mean by flat end? One of the familiar minimal surfaces you may know is the catenoid, which is the surface of revolution that's, take a catenary and revolve it around the axis. But the thing is, the ends here are not asymptotic to a plane. They actually sort of grow logarithmically. It's kind of a very flat, and they're not really cones either because it doesn't grow linearly, it grows logarithmically. But it's not asymptotic to a plane, and that's what flat end means. And in fact, if you take the catenoid like this, here's a couple of pictures of the catenoid, and if you invert, say, through the center here, those ends will then be brought into 0, and it'll actually complete to be a C1 surface. They'll come in, they'll look like this, it'll actually be C1, the two ends will touch each other, but in fact it's not hard to prove that it's only C1, it's not C2. It's not even twice differentiable at the origin. So the catenoid never shows up in this story. And in fact, it turns out that you can't have a Wilmore sphere that has 8 pi because that would be these with only 2 ends. Because the next theorem I proved was that if it's genus 0 and it's an immersed Wilmore surface with WS equals 4 pi m, and m is the maximum multiplicity, and m is less than or equal to 8, then m can only be 1, 4, 6, or 8. It can't be 2, can't be 3, can't be 5, can't be 7. And this was using what we know about minimal surfaces with flat ends. It turns out that there's a big technology with complete minimal surfaces that I don't have time to talk about, but this basically reduced to an algebra problem to do this, a very complicated algebra problem. And in fact, I'll just remark that the only known examples with m bigger than 8 have m even. And every even m does occur. You can actually write down examples, even-ended examples. And for a long time, there were claims in the literature that every number bigger than 8 occurs. That is, there was a claimed paper that supposedly produced 9, 11, 13, and so on like that. But a student of Tristan Revere recently showed that, in fact, that paper is erroneous. There's an error in that paper that invalidates all the results. And in fact, he was able to, and of course, that doesn't mean that there aren't any odd ones. It just means that construction didn't work. But he was able to show that actually 9 is ruled out. 9 can't happen by sort of jazzing up what I did to rule out 5 and 7. But it's algebraically extremely complicated. I doubt anybody will ever use this method to prove that 11 cannot be found. But we're wondering whether or not there is an 11, actually. That's still unknown. But there is a positive consequence of this, which is this. Remember I said that if you had an RP2 that's Wilmore, then its Wilmore thing is at least 12 pi. And if you had 12 pi, so if you double cover it to get a sphere, then of course the Wilmore integram will double, and you'll get 24 pi, which is 4 pi times 6. So what you might hope is that there might be a Wilmore RP2 with 3 sheets going through one point. We know there have to be at least 3. That when you double it, you get a 6 multiplicity Wilmore sphere. And conversely, if you can find a 6 multiplicity Wilmore sphere that's invariant under the antipodal map, then you'll find an RP2. And in fact, that's exactly what Rob Kussner and I did independently a few years ago. Well, a long time ago now. We actually constructed a Wilmore RP2 that has exactly 12 pi, and we did an explicit construction. There's I'm almost out of time. I want to let me show you a picture of. Whoops, what is this? I don't know that. You know, if you make RP2 by dividing the sphere by the antipodal map, it's hard to visualize what that looks like, but you can do the following thing. First, ignore the north and south poles and just look at a band around the equator. If you take a band around the equator and identify opposite points, what you'll get is a Möbius strip, right? Imagine just take the front half of it and identify the ends with the reverse. You get a Möbius strip. And so what this is a picture of is the surface that we found that minimizes the bending energy. This is a picture of the Möbius strip, the equatorial band. You can see that this actually is a Möbius band, and it has a threefold symmetry. But you can, if you want to see how to put the cap on, that's the hard part, right? Because once you do this, you have a surface that has one edge that's a circle, and all you have to do is put a cap on it. But it's not so obvious how you could ever stitch it on without running into itself and stuff like that. But this draws a picture of what that looks like, and I'll just show you as it thickens to go out to the pole. There's the triple point. You can see that now it's easy to see how to put the cap on, right? I'll run it one more time here. And you'll notice that it's very symmetric. It doesn't have any pinch points or weird looking, there's very little, whoops, I lost it. But that's okay. I should go back to, I should finish up my talk. There's a lot of, there are in fact a lot of pictures of the surface on the web. If you go and look, just Google Bryant-Kussner, and you'll see lots of movies and things like that show you exactly what it looks like. 3D images you can put on these 3D glasses and see the whole thing spinning around. It's pretty cool. But here's the funny thing. So you might think, well, that's the unique one, right? But unfortunately, it turns out that the space of all minima when you actually do the calculation and run through it, it turns out that this Wilmore guy is not unique, even up to conformal transformation. Even after you divide out by conformal transformations, there's still a 2-parameter family, a non-compact 2-parameter family that of inequivalent minima for the Wilmore surface. And in fact, as you go to the boundary in this non-compact thing, what happens is it develops a singularity. So Leon Simon's idea of reducing to the embedded case and being able to avoid development of singularities and things like that, unfortunately, is not going to work for the unorientable surfaces. For the unorientable surfaces, there's no way that you can, by doing some kind of control, avoid a minimizing sequence developing a singularity, because even right at the minimum, you can develop a singularity, unfortunately. So the unorientable cases remain a challenge. We really don't have a good idea at the moment. And I just, but now finally, in the last few minutes, let me say what the big news is. 6 years ago, Marquez and Neves were able to prove the Wilmore conjecture. That is, I should say, the modified Wilmore conjecture, because remember we saw that the minimum is not just the anchor ring, because it can look like one of these weird bulged things, but up to conformal transformation, it is unique. And that's what the true Wilmore conjecture is, which is that, that's what the true theorem is, which they proved in 2012, is that the Wilmore integrand is at least 2 pi squared for a torus, and equality happens if and only if it's conformally equivalent to the anchor ring torus with aspect ratio 1 to 2, 1 to square root 2. I'm out of time, so I really can't give you much of a sketch of the proof. The proof's about 100 pages long in the annals. It's highly ingenious and a real tour de force. But the basic idea is that they have to play off the non-compactness of the conformal group with being able to normalize out minimizers. And it turns out that the ideas that turn out to be relevant are this Almgren and Pitt's theory of min-max constructions. That is, you minimize something that's been maximized to construct the sequence that you hope has a convergent subsequence. And their techniques and ideas have really opened a new chapter in the calculus of variations. It's been an eye-opening experience to see it. The ideas now being applied in all kinds of to study lots of different problems. It's very hopeful. The second remark is the story's not over. First of all, we still don't know what happens in higher genus. We don't know. We don't really. Nobody has made a bold conjecture as to what would, for the two-hole torus, be the best possible shape. There is the only real candidate that I know of is Lawson's construction of a minimal two-hole torus in the three-sphere that actually looks pretty nice, but we're a long ways from being able to prove that is the minimum. As I was saying, in a non-orientable case, we really don't have any control over the kinds of singularities that can be developed. We need new tools for understanding those things. And in higher dimensions, that is, all this work to find the best shape of a surface in R3, but what about the best shape of the surface in R4? For example, it turns out that if you consider the same thing in R4 as, what's the minimum total bending energy of an RP2 in R4, it turns out that you can get down to 6 pi. You don't have to go to 12 pi. But then it turns out that you can't do any better than that. It's always, no matter how much higher in dimension you go, the lowest total bending is 6 pi for RP2. But in order to make any real progress on this, you have to really grapple with this kind of singularity, the difficulties of singularity development. And Tristan Rivière, which I realize I have another misprint here, there should be an E accent there, has made some real progress in controlling these kinds of singularities by starting with surface without assuming the surface is smooth, but only C1. and being able to integrate by parts to avoid having to deal with the two derivatives that the Wilmore functional is actually defined in terms of. It's a rather a bold program. He's been making some amazing progress on it in the last few years, and I think that so in particular he can deal with sequences that converge to something like the inverted catenoid. It's a really interesting development, and probably any significant progress is going to lead us through that patch. But the papers are not easy to read by any means. Anyway, thank you for your patience. I hope I'm happy to answer questions.